here. All right. Hopefully this will be better. All right. Let's see. Nobody's back yet. All right, they're coming back. Pardon me. I'll turn on the light too. All right, I guess I better wait another minute or so. Ah, here come more people. Okay, fair enough. I think we got up to 5 before, so there's probably one more coming. I'll wait another minute and then go ahead. All right, I think we've got who we're going to get. So let me, yep, somebody dropped out. Maybe they will come back. So the first part here, we got down to these cahoots, and I wanted to start with them. So that was here at the end of information models, and I've got that here now. So that would be this. All right. So join that, 88074. All right, good. Got 2 people. I think there's one more. Probably Jeffrey. And I wouldn't be surprised if KT came back. Here's KT. Yeah, so 2 people may wish to join this Kahoot. 88074. Maybe 3 more people. Okay. There we go. We got 4 people. I'll wait another 10 seconds to see if the last one's going to join up. All right, I think that's how many we've got. So, 4 questions here. All right, which model gives you confidentiality but not integrity? All right, that's Bell LaPadula. It was the first model. It's also first in alphabetical order of Bell, Biba, and Clark. These are the three big ones you'll certainly see on the exam. All right. All right, which one had the alpha, beta, gamma access? All right, that was the lattice model, not the Clark-Wilson, one that I haven't seen that commonly. All right, which one has no read up? All right, that's Bell LaPadula because it has confidentiality. You can't read things at a higher level of clearance. All right, which one has no read down? Okay, that's BIBA. So anyway, the way I memorized these back when I took the CISSP is alphabetical order, Bell, BIBA, and Clark. And the first one gives you only in confidentiality, which is the first thing people think about in security. The next one gives you only integrity. And the third one, Clark-Wilson, is the realistic one you can actually do business with by not going to either of those extremes. All right. So I think you didn't see the slides for this, so I'm going to go through it a little bit here, and then we'll do the Kahoot at the end, and hopefully that'll get you to where you've seen it. This is just sort of a grab bag of other models. So information flow is a category that includes these models like Bell and Bell LaPadula and BIBA that are watching how the information flows from one state to another of the state machine. The Chinese wall we talked about is a way to limit how information moves within an organization so you can hopefully avoid conflicts of interest even when you are pursuing two activities that might conflict. Non-interference is the property where a high security activity will not change anything measurable about a low security issue, so you cannot observe low security things and deduce high security facts from them. The take grant rule model is another one that has these rules where people can have a complex model of interactions. So there are secrets here, and Alice can grant Carol permissions, but then Bob can take away Alice's permissions. So you have, I think you can create this with Microsoft Windows domains too, where people have an interlocked mesh of permissions, including permissions to change permissions. And of course, once you start getting this complicated, it's pretty easy to have unexpected consequences. So in the real world, a Windows domain controller Microsoft certification tells you, don't get too fancy. Have a few simple groups and clearly defined roles, or you will rapidly create a mess where it's hard to figure out who's letting you do things. So you can have a matrix of access control listing users and what they're allowed to do to various things like applications and files. And there are other frameworks specified particularly for business, where here you have all these different roles that you might serve at the business, and then all these parts of the business that matter, and all these documents and policies you could have to control all these things. This is one possible way to organize your information security. Here's another one with the Graham-Denning model, where people have 8 rules whether you can destroy objects or create or destroy a subject, or grant access or transfer access, and so on. These are just possible formal rules to control the operation inside systems, and these papers and research projects are to figure out whether these rules are a reasonable way to design something like an operating system. And the HRU model is similar, with just a different set of possible rules here, like enter right in access matrix, delete right from access matrix, and so on. This is the one just before people told me the slides weren't showing. So these are the 4 modes of operation for mandatory access control environments. The simplest and oldest is the dedicated model, where you have to have separate hardware for every level, and nobody is allowed to touch the secret hardware except people that are cleared for secret, and so on with top secret and classified. This is easy to understand, but it's kind of expensive and inconvenient. And of course, the dirty little secret is you can't have computers that have no way to put data on them at all. So what people really use is USB drives. And we and the Israelis with Stuxnet figured out how to cross air gaps by infecting USB drives. So you have sort of a serious problem here. You have to somehow move the data from one machine to another without compromising the security, and that's not easy. So these other models actually do put multiple levels of security on the same machine and separate it in software. So here's the system high level, where you have mixed objects on the same machine, but you make sure that all the people are cleared to the highest level on the machine, so you don't have to trust the operating system to really protect your secrets. And here's the compartmented level, where everyone has clearance, but they don't necessarily have the horizontal controls like need to know, and so you trust the software to do the perhaps less important horizontal controls, but not the vertical controls. And the multi-level, where you actually trust the software to do everything. It's got multiple sensitivity labels and multiple horizontal labels on all the objects, and the reference monitor is controlling all this. All right. So anyway, the certification models are TC-SEC. This is the one referred to most often in all the CISSP books I've read. This is the military 1980s Orange Book. And it specified a lot of terms which then became the industry terms, like the trusted platform module and so on, for computer security. People named modules on hardware after the function they would serve to meet this specification so they could sell their devices to the military and to military contractors. So A is the best, and I should talk more about these than I did before. So D is minimal protection, like MS-DOS. C is discretionary protection, where you have owners of objects and the owners can do whatever they want with them, which is typical for a home computer. The owner can give access to any file or the hardware itself to anybody they want. Then you have mandatory protection. This is mandatory access control instead of discretionary access control, where the people are labeled and the information is labeled and the computers are labeled, and you have to go through a formal process to move from one label to another. So you have to be cleared for a higher level before you can access certain devices, and you have to declassify information before it can be made available to other people. So this is called mandatory access control, and it's what you think of in the military. And the highest level, A, is in the realm of, say, ISO 27000 certification, where not only do you do all these good things, but you have an administrative process of review. So you make security policies, you implement them, you document that you've done that, you then measure compliance with the policies, you then plan how to improve your policies so as to improve overall security and keep it continuously adapting as the industry and hardware and everything change. And that is verified protection, where not only do you have all the lower levels of protection, but you have a whole bunch of filed documents and layers of oversight and administration to prove that you are maintaining that. And then you can be trusted with highly secure objects. So an alternative is the Red Book. This was the Red Book part of the series for networking in the same vein. And then there was ITSEC from Europe, which accomplished approximately the same job, but it had two levels, functionality and assurance levels. So you ended up with a different series of letters to describe this. So E0 was inadequate, and E6 was where you had a formal model of security policy, roughly equivalent to the Orange Book levels. And here's how they would match. A1 is up here at FB3 or E6. That's the highest level, and the lowest level down here that an American would call D, the Europeans would call E0, and so it goes, with a few special cases. And then eventually, we established an international common criteria. And the idea here was to have one that would apply to both the US and Europe, since we're going to work together. And so they have this thing called the target of evaluation, which is the product you're evaluating, and the security target, which defines what level of security you're trying to accomplish. And then they can analyze your system and decide if it meets that level or not. And so you have a protection profile, which is defined for various objects, and you have an evaluation assurance level, which shows to what extent you actually achieve those goals. And here's the levels of it. The highest is EAL7, which is again formally verified. There has been a security review designed and tested. Every stage of producing and maintaining this system have several layers of management. Analyze, make sure that it's meeting your criteria and that you're constantly improving it to keep up with changes. EAL1 is your lowest level, where all you do is make sure it works and you don't worry about anything else like security or maintainability. All right, which is, I must say, I've been doing a lot of Android app security, and it is abundantly clear to me that almost all Android apps never go any higher than EAL1. As long as they work as intended when used in a normal context, they don't look any further at what's happening because their security is appalling. Anyway, I got some cahoots for this stuff. Bring them up. If I can get this out of the way, that's what got me before. Okay, we're up to number 2 here. All right. There we go. Kahoot seems to be so popular, they have 7-digit numbers now. 156 5786. Pardon me. All right. I think KT is normally a Kahooter. Let's wait a few seconds and see if she joins us. Or he. All right, I'm waiting 5 more seconds. All right. Ah, there she is. Good. I think we got the full complement. Jeffrey does not seem to be a Kahooter. All right, 5 questions. So what feature prevents a covert channel? All right, that's non-interference. All right. Which operation enforces an air gap between each security level? All right, your system has to, not a popular answer, that's dedicated. You have a dedicated system for top secret and another dedicated system for secret and classified and unclassified. That's the simplest model where you don't really trust the internal computer security much at all, and you keep an air gap between the levels. All right. Which operation mode has the reference monitor? All right, that's multi-level, where you're trusting the operating system to do all the parsing, so it has to have a component called a reference monitor that really makes sure that only the top secret people are seeing the top secret things, and so on. All right, now, what's the TC-SEC level for a home Windows 10 laptop? All right, we're all over the place. A is the highest level, and Windows 10 and a home user certainly doesn't have that. It's C. D is the lowest level, and Windows 10, ever since, because it's based on Windows NT, it does have some degree of access control that brings it up to a C. You can put permissions on objects, but in order for it to be a B, it would have to have a mandatory access control environment, so you had to go to some kind of supervisor to get permission to see the objects. And in order to reach A, it would have to have a whole bunch of administrative controls to prove that all of its security properties have been measured and are constantly being improved. All right, let's try another one. What's the modern international method? Right, it's the common criteria, a somewhat popular answer. All right, well, you guys taking the test will have to review that stuff a bit more, I reckon. All right, let's move ahead a bit here. All right, so here's system design concepts. One of them is layering. You separate things into layers like the OSI model and many other things, and the point here is you can focus on one layer. You make the hardware, then you have the lowest level of software, the device drivers and the kernel that directly control the hardware, and then you have the operating system above that that doesn't directly touch the hardware. It goes through device drivers and the kernel to get to the hardware, and then user applications right on top of the operating system and communicate only through the other stages. This turns out to be the most effective way to allow each programmer and developer to focus on just a smaller subset of problems. One general security property here is abstraction, where you do not bother people with information that will just confuse them. So users don't really know about the hard drive and the RAM and the bus and the processor. They just see a desktop with a picture of a web page or a Word document, and they just double click on it and use it, and they do not worry about the complexity that is removed from the screen and taken out of their view. All right. You have security domains. Kernel mode is the lowest level mode, which has direct access to the hardware. And user mode is where everything the user launches once they've logged in happens, and none of that has direct access to the hardware. All it can do is ask something like a device driver or kernel module to please do something, and it does it on your behalf. The idea here is that if there's errors in user mode software, it can't affect kernel mode. So normally, if an application crashes, like your browser or Microsoft Word, it doesn't bring the whole machine down. It just causes one process to crash, and your other processes can't continue. The ring model is built into the processor. Intel processors and their equivalents have these 4 rings. The only 2 that are actually used, however, by any modern operating system are 0 and 3. Ring 0 is kernel mode, directly connected to the hardware. Ring 3 is user mode, and they do not have access to all the machine language instructions in Ring 3. In order to protect the operating system, to do certain things, they have to ask the Ring 0 routines to please do that for you. And the developer of your operating system pays great attention to the security of the kernel so that it is hard for you to crash the machine. Now some people have this thing called Ring 1, although I'm not sure if it actually uses Ring 1 of that model, but this is hardware-assisted virtualization. And modern virtualization products like VMware require this. This allows virtual guests to run much faster. And it's controlled by a feature called the hypervisor. People call it Intel VT and AMD V. It's in the BIOS of machines, and it seems to usually be deactivated by default. Open systems are ones that publish the specifications of the operating system and the chips so you can build your own, like the IBM PC. Closed systems like Apple, before they switched to Intel, would not let you know anything about the hardware or, for that matter, the software. So they had sort of a monopoly control over the device. All right. Your system unit is the computer's case that contains things like the hard drive and the RAM. The motherboard is the main circuit board in at least the old desktop machines, and it's still true of laptops. These are the CPU, RAM, and firmware, which runs things like the keyboard and the network card and peripheral slots to add more components. The bus is just the copper lines that move data around on the machine. There are various levels of bus moving data from the CPU to the display and the RAM and the keyboard back and forth. In these days, they talk about Northbridge and Southbridge, where they have 2 buses. The Northbridge faster line is used for things like the video card that really have to get a lot of data fast. The Southbridge that's slower is used for things like the keyboard, and the CD where it really doesn't have to be so fast. The CPU is the component that does all the processing. The arithmetic logic unit performs math and logical operations like XOR and the control unit is another part of the CPU which fetches instructions from RAM and passes them on to the ALU for processing. So there's the CPU cycle. You fetch an instruction, you decode it into the raw bits that it's going to need to have to process it, then you execute it in the CPU, then you take the result and save it somewhere, and that's the clock cycle. Most instructions on the modern processor take several clock cycles, like 6 or 8. Interrupts are demands for immediate attention. They've been around for a long time, since the old MS-DOS machines, and so computers are constantly stopping what they're doing and doing something else. The interrupt will tell you something like something is coming in on the network card, or something, the user is pressing a key, and so on. Something has happened, which means you should suspend normal operation and deal with this event. Each application you launch on the machine is a process. A typical Windows machine has 50 or 60 processes running even before you start launching applications. And the actual units that do work on the machine are called threads. Every process is broken up into multiple threads so that the threads can proceed. The one huge problem in computing is you have a fast object that is slowed down waiting for a slow object to move. And this happens at many levels. The CPU is running at 2 or 3 gigahertz, but the memory takes something like 50 or 60 nanoseconds to remember something. So when the CPU is trying to save data in RAM or read data from RAM, it's just tapping its foot waiting for the RAM to respond. The hard drive is much slower. The CD and the keyboard and the mouse are much slower again. So very often your computer is waiting for something very slow to happen. So you compensate for this by breaking every process up into small processes called threads that can move forward independently, so that if one thread is waiting for a slow thing to happen, the other threads can at least keep moving, so you don't waste your CPU as much. It's able to make some kind of progress on whatever portion of the program is ready to move forward. Multitasking and multiprocessing are also used on these modern systems. They're all multitasking now. They run many programs at once. I don't know how many of you are old enough to have used the original MS-DOS, but I remember you'd have a Word document, you would hit print, and then you would go get a cup of coffee, because while it's printing, you can't do anything. You can't open up any other window or do anything else. It can only be doing one thing. It can be processing a Word document, or it can be printing it, but that's it. Now they have multiprocessing, of course, multitasking, I should say. You can close a window and open another window and do many things at once. The processor isn't really doing more than one thing at a time, but it flips quickly from one window to another, so they all move forward. Multiprocessing is using multiple processors to move forward, and most modern computers are dual core or 4-core. There's actually several CPU cores in there working all at once. You've got a timer here, which watches to see if a critical process is not moving forward anymore. It can figure out that the operating system has crashed, and it's going to have to just reboot the system. The computers, almost all computers now use the CISC model from Intel, where there are something like 10,000 actual instructions on the CPU. There is another model used by older Apple computers with Motorola processors called reduced instruction set, where they cut down the number of repetitive instructions to a smaller number to try to make them faster. And I think ARMs on cell phones still use that model. Both of these accomplish the same goal, but some people think that the RISC computer might be saving power and time. So you've got memory addressing. You can have direct addressing, like you see here in the first one, where you have refer in the machine language instruction. You add X plus some number in Y. The address is right there in the instruction. Then you have indirect addressing, where the address you put in the instruction goes to a pointer, which then points to another location. And then you can have a direct reference to a register. The registers are little bits of memory stored right on the processor, like register EAX, EBX, and so on. Or register can contain an address. So the instruction will go to the register, find the address, and then go to that location in RAM to find the memory you're referring to. And all these are important and used. One process cannot affect another process. This is the plan. Each process is allocated a certain amount of memory, and it's not allowed to write on somebody else's memory. This is called process isolation, and it's done typically with virtual memory. There are some other techniques like object encapsulation. Another issue is, of course, that each process gets different slices of time, so the processor knows which process is working on at each time and what restrictions to place on its activities. When you start a Intel-based machine, it starts in real mode, which is the really old thing. And this is where there's no process isolation and you can only use a small amount of memory. And it's used during the early stage of startup when you see text messages scroll by on the screen. Then, after a certain point, it switches to protected mode, although the 64-bit processor operates in a different way. Virtual memory maps processes and hardware memory. Almost all Windows applications believe that they are loaded to the same location, 400,000 in hexadecimal. They are working with virtual memory addresses, so they cannot refer to memory outside their allocated range. That's the plan. If you try to access memory, if you keep opening applications until you've used up all the available physical RAM, you can continue to open applications, and pages of RAM are written to the hard disk, or the SSD these days. That's called swapping. It makes the computer able to act as if it had more memory than it really has. But what happens is when you try to go back to a process and the memory has been written to the hard disk, that's called a page fault, and it has to wait while it reloads that back into RAM. So you lose performance when you run in this mode. And this is why most people find you improve computers by adding more RAM to them, so you have less paging going on. The BIOS controls the hardware when you first start the machine. It hunts around to try to find a hard disk and a keyboard and a monitor and so on. That's the power on self test. If it does find some kind of hard disk or SSD to boot from, it then boots up. Worm storage are things that can be written, but they cannot be erased, like CDs and DVDs of the original type. All right. Trusted Platform Module is named after a component in the Orange Book. It is the cryptographic processor on the motherboard that can securely store keys. An analogous element is called the secure element on an iPhone and on the more expensive Android phones. And this is a special hardware chip to store cryptographic keys. And the reason it's so important is the keys are not anywhere in the address space of the primary processor. So no possible program or malware running on your computer can possibly store the key. There is no address where it is. All your program can do is ask the TPM to please decrypt this stuff. And it will do it, but you can't get at the key that's on there. And this can also be used to detect rootkits on boot up, because it can check the cryptographic sum, integrity check, a hash value of the kernel on boot up, and compare it to some information in the TPM that can't be altered. Data execution prevention is an important security feature added to Microsoft Windows machines in Windows XP Service Pack 2, where parts of RAM can be marked non-executable. This prevented buffer overflow attacks. If an attacker lets you put in too much data into something like a password field so you can inject code, the next step is to run that code. But if you have a machine with data execution prevention operating, the injected code will just sit there, and when you try to run it, it will not execute because you have permissions on the RAM. The other one, defense that really protected Microsoft Windows machines, starting with Vista, was address space layout randomization. So instead of every process just using the next available RAM, it randomly uses RAM, so that every time you reboot the machine, all the processes are randomly scrambled in memory. This means that if an attacker finds a way to inject code, they can't find where the code is to run it later. And this did slow down attacks for a whole year on Vista at the Canada Pwned conference. All right, I got some cahoots about that. Let's see how you like that. Hardware stuff. Get this down here and go here to cahoots number 3. All right. Stop that. Okay. All right. we are, 3 people. Let's see how many I've got. 6, my goodness. Yes, so I think I should get at least 1 more. There we are. I think that's how it's going. We're getting 4. Jeff is a non-cahooter, apparently. Okay. 5 questions. All right, what CPU ring is user mode in? All right, that's ring 3. Good, the popular answer is correct. All right, so users can't handle the truth and the computer lies to them. What term is used for that? All right, that's abstraction. You are told only what is appropriate for you to know. All right. What's communication channel between components? All right, that's the bus. Good. All right. I launched Microsoft Word. What is that? That's a process. Each process contains many threads, but Word itself is a process. All right. Where's the cryptographic coprocessor? All right, the trusted platform module. That's it? Okay, good. KT is the winner, I see, although it looks pretty close. All right. So let's go back and do some more of this. All right. So the kernel is the heart of the operating system running in ring 0. There are 2 types of kernel, monolithic and microkernel. General purpose operating systems like Windows use the monolithic type. This is, wait a minute now. No, I'm sorry, I mixed up the other kind. So the monolithic is where the entire kernel is one static executable and you have to recompile it to add any more features. This is appropriate for hardware devices like routers. The microkernel is the other kind that has less native functionality. I think I'm going to have to be careful here. I'm not sure which one Microsoft Windows uses. I shouldn't jump into this. I know you could put loaded kernel modules on Linux machines and the Mac, and you can put them on the old coprocessors from Novell. But anyway, so these are the modular ones that have less native functionality, but they can have loadable kernel modules adding, and they might mix some Ring 3 modules in. I'm pretty sure Windows uses the monolithic one, though. Anyway, the reference monitor we talked about before is a software component that is making sure that all the users only access objects that they are cleared to use, enforcing the security policy. It has to be always enabled and not bypassable, or you will not make it to levels A or B of the TC-SEC. You have, in Linux, you have permissions like read, write, and execute. If you do ls-l, you'll start with this string where a D or a dash tells you if it's a directory or file, and then you have read, write, execute for user, read, write, execute for members of the same group, and read, write, execute for everybody else. That string of 9 letters specifies the levels of permission. It is a very simple permission structure, much simpler than the Microsoft one, which is more complicated here. In the Microsoft one, you have groups of people like everyone and administrators and interactive users and system and as many groups as you want. And then each one of those has a whole bunch of permissions like full control, modify, read and execute, and so on. So it's a much more complex and rich structure intended for real business. And on domain controllers, this is why you have it. You can make as complicated a model of your business as you have to meet your objectives. All right, there are privileged programs which run at higher security levels. In Linux world, these are called setuid files, such as password that changes your password. The password file is only accessible to high privileged users, but even low privileged users have to be able to change their own password. So they run this password file, which runs not with the privileges of the user that launched it, but the privileges of the owner. And these things are risky because if you can make the computer crash while it's in the high privilege mode, you've got a privilege escalation attack. And these things are quite common. See, I'm hearing funny noises. I ought to try muting people so they don't irritate one another. Well, let's see what that does. All right. Anyway, so let me see if I can get this thing out of the way. Just a moment. There. All right. Now we should be back on the road. All right. So virtualization is, of course, a big issue. Virtualization, you run a program on your machine called a hypervisor, which simulates hardware, and then you install another operating system on the simulated hardware, so it sees a simulated hard disk and CPU and RAM and runs. Full virtualization is what I've described, so you might simulate hardware that is completely different than the real hardware underneath. An alternative is para-virtualization, where you actually connect the virtual hardware to the real hardware. This is less versatile, but it might run faster and be more efficient. The hypervisor is the software that makes the bridge between the guest OS and the host hardware. Type 1 hypervisor is running directly on the host hardware, which is what VMware does with its ESXi product used for enterprise class servers. Consumer and end user devices use things like VMware Workstation, which runs as an application in user land, like Microsoft Word. And so it's actually less efficient and slower, but it cooperates more with other programs you might want to run on your machine. So this turns out to be enormously beneficial. I remember when this all started, for me, it was in 2004 with Microsoft's virtualization product called Virtual PC, and we got it running, and then we looked at it and we said, why would anybody want to do this? You got a computer, why do you want to have another computer? And then after a while, we started to see all the great stuff you can do. You can test software, you can run viruses, you can simulate a whole network and practice a complicated situation, so it became quite popular. Enterprise users had been on it for years, because it means they don't have to keep buying identical servers with identical hardware. They can keep modernizing their servers, and they can even mix old hardware and new hardware and make the virtual hardware all the same. It turns out to be enormously valuable. So running many guests on one host is quite common. These guests are therefore not perfectly separated from one another. Obviously, if the main operating system underneath crashes or the power goes out, all the guests will go down. And also, the hypervisor is not perfect, like a reference monitor should be. It does not 100% prevent software in the guest from creeping into the host or from creeping into another virtual machine. And that's called a VM escape attack, when you escape your virtual environment and move around to other machines, other parts of the system, and those things do happen. Another issue is if you have two virtual machines and they send network traffic to each other, it doesn't actually go out any physical network card, so you won't be able to see it and send it to your network intrusion detection system. So as you move to software-defined networks and simulated networks, you lose visibility unless you then put in virtual forwarders to capture the virtual traffic and send it somewhere for analysis. So this gets us into cloud computing as you're using more and more resources on someone else's machine far away over the internet. Infrastructure as a service is where you can rent a physical machine somewhere else, or for that matter, a virtual machine. Platform as a service gives you a software environment that you can design things and put them on, like web hosting, where the service provider gives you a certain amount of bandwidth and a certain amount of hard disk space, and you can put whatever web pages you want on there. And then there's software as a service, where you have to just use the options the programmer gives you, like Gmail. You can do certain things, but you don't really have real control over the files that are stored or over the processor. You can't write your own software and run it on it. You just have to use whatever features they feel like giving you. Private clouds are what people need if they want to have good control of their data. For example, if you use Windows Azure, Microsoft will tell you that they do not even know how many copies of your data there are, or even what country they're in. So if your data is sensitive or confidential or military, then it's really not appropriate to put it on Azure unless you pay for a higher privilege level where they promise to make sure at least you'll know what country it's in. The cheapest level is always the public cloud, where if you just get an Amazon instance, then it just runs, but you don't even really know where it is or how many copies there are or how it's being backed up or anything like that. And most people don't care that much, but they do care about it staying up. So there's a service level agreement for how much it will stay up and how many hours it's tolerable for it to go down. And you are also service level agreements for security. You can get an Amazon instance that is guaranteed to meet HIPAA requirements. And they promise that, and you then have some liability on them if they fail to do that. Amazon has had security problems, quite a few of them. There was a public image that was distributed with a backdoor account. You can go through a menu and get an operating system, and one of them was distributed with a known SSH key. Also, when the Amazon infrastructure was new, there was a security researcher that got a new machine and ran a forensic tool, and he found out that the data from the previous user was still there. Amazon was not cleaning the images when releasing them from deployment and handing them off to the next person. So people have concerns about the security of the public cloud, and those concerns are justified. Grid computing is another issue that happens over the internet, where you get many people to donate computing power to a big project, and now they might be totally dissimilar systems. This is what Bitcoin does. It runs on many machines all working together, and so does SETI at home and quite a few other projects. Parallel systems give you high performance, but they share memory between systems. So you can have race conditions where one process is writing to memory and another process is also writing to memory. And when the first one comes back and tries to read what it wrote, it has been changed. This led to, I think, the dirty cow exploit and a bunch of security exploits. These are called race conditions because the attacker has to win the race. And if they manage to get in first, they can change the behavior of a program. Peer-to-peer sharing, like BitTorrent, is another example of computing over the internet. The point of it is it's very difficult to take down. If a bunch of people are sharing a copyrighted movie, there is not any one server anywhere which you can unplug or seize to stop it until there are many copies of it flying around all over the place. There are some integrity controls in BitTorrent, but it is in general very dangerous to use because a lot of the torrents come down with malware in them. And in addition, they're almost always illegal anyway, violating copyright rules at least. Thin clients are quite popular now. You do virtual desktop infrastructure where you're actually just viewing a machine that is running on a server and all the data is staying on the server, and your computer is really just used as a portal to view it, so the hardware requirements for your computer are quite small. They call that a thin client. You often just run a web browser and remote control it elsewhere. This is quite good for the company because all they have to do is secure the server. They don't have to worry about extra copies of the data being on everybody's laptop. And there are diskless workstations that just don't even have a disk or much of an operating system at all. They're just dependent on the server doing all the work. The Internet of Things, of course, is all the consumer devices and other devices being designed, connecting things to the internet that never used to be on the internet, like refrigerators. Unfortunately, the first generation of this stuff is generally designed with no security at all, so it often has default passwords or no passwords, no way to update them, and so on. So there have been many attacks like the Mirai botnet involving taking over thousands or millions of these insecure devices that are proliferating through the world. And there are some cahoots, but I haven't got these up there yet, so we'll do these next time. And then there's vulnerabilities here, the threats and countermeasures. Emanations are the radio signals that leak from your computer devices. The Tempest project from the US government showed that, in fact, you can see every key press, you can see everything that appears on an old CRT screen. If you really don't want everyone knowing what you're doing, you pretty much have to be in a basement room with no windows and metal all around you. There are a lot of covert channels that leak data out. There are storage channels. A lot of people share data in the temp folder, and that's one, then other people can see it. Even if you don't store data on a hard drive in the temp folder, another person could just ask the disk how full it is, and they could find out how big a file you stored is by watching how much space went away. Then there's timing channels. You can identify the physical location of someone on the internet by timing how long it takes for the pings and other packets to get there and come back. And there are other things like that. The time to reject a username is different if you have a good password and a bad password. So there's a lot of tricks here that you can use to leak information out. And there's backdoors. There are often special ways to take over a machine. Sometimes these are there for developers to have maintenance. Often developers forget to remove the maintenance hooks when the systems go to deployment. And of course, the FBI is always asking for the government to have backdoors so that when they come to you with a search warrant, you can hand over the real data. And most companies have had them, at least for their tech support division. It's in the last couple of years, Apple is trying to get rid of their own backdoors so even they can't get in, and the FBI is very upset about that. So malware infects your machine. Most of them are using known attacks, but the ones that are not known are called zero-day attacks because you had zero time to patch them and there's no way to stop them. But zero-day exploits are very rarely used against normal users. They're primarily used by nation states and military against high-value targets because the more you use a zero-day, the more you use it up. As soon as somebody catches a sample and sends it to an antivirus company, then it's no longer a zero-day and it pretty much becomes useless as everybody patches it. Viruses are a very old threat from the days of floppy disks attached to an executable file. More modern things are macro viruses in Microsoft Office documents. There's boot sector viruses used to be on floppies, and some viruses mutate to change every time to avoid antivirus engines, and some spread through multiple vectors, like they spread through file shares and email and instant messages and hide in the printer. Those have been around for about 20 years now. Worms are things that propagate over the network without being attached to a file with things like instant messages or email attachments. Trojans deceive you. The most common type is fake antivirus. You install it and it's actually malware hurting you. Rootkits replace the kernel with fake kernel routines, or at least bad addresses for kernel routines, so that now if you do something like run a directory of the disk or run antivirus software, it doesn't work anymore because the kernel lies to it about what's on the disk. Rootkits are what criminals use to maintain permanent ownership of a machine. They can just come back, rebooting does nothing, and often they're very hard to detect and very hard to remove. Packers are things that obfuscate executables. The simplest packer is zip. As you know, there are self-extracting zip archives. So you have a compressed file, and when you run it, the first thing it does is unzip itself. Packers just continue the same system. One common one is UPX, and the point of them is not really to make things smaller, but to scramble the bits so antivirus engines can't detect the malware in them. Logic bombs are programs that wait for a trigger condition and then execute a payload. Like on a certain date, they wipe out the hard drive, or they scan your employee directory to see if you fired the disgruntled employee that put it there, and as soon as they're not getting a paycheck, then it wipes out your system. There's one of these on Fannie Mae to wipe everything out, and somehow they found it before it wiped out Fannie Mae's systems. These are very hard to find because they're custom written. Antivirus is not going to find them. Your antivirus software is almost always signature-based. Where it's just looking for known bad programs, so it's really only stopping yesterday's attack. They have some very limited ability to detect unusual, suspicious behavior without recognizing the exact malware, but in practice, the sensitivity of that process is almost always very low because otherwise it will flag innocent software and call it viruses, and that really annoys people, so they set the sensitivity so that there are very few of those false positives. You can exploit vulnerable services on a server. If your server is offering SMB file sharing over the internet, which is a terrible idea, there are a bunch of attacks that will take it over, and you abuse that by sending some kind of deformed packets up to that port. In client-side attacks, you have a program that is vulnerable running on your machine, but it's not listening on a network, so the only way to do it is to include social engineering. You somehow trick a user into running something, like send them a PDF file or something, and then somebody has to run it, and then it can exploit a local program which was not intended to be doing networking. Active content on the web, on your web pages, like you have on Facebook, where users can post comments and other users see them, introduces new vulnerabilities. WordPress and many other web sites run PHP, and PHP is famous for file inclusion vulnerabilities. And very commonly in PHP, you see URLs like this. You go to some page, index.php, and then you have a parameter with a file name in it. So you can often change that parameter to point to another file on the same server or even on a different server, and you can create a URL that appears to come from one domain, but in fact contains content from another. And that can infect people because their browser will trust it, thinking it's part of a trusted domain when it isn't. Java applets are extremely dangerous, and I think most people have now quit using Java on their home devices and on end-user workstations. Java remains popular on servers because of its cross-platform nature, but on the Java virtual machine on individual browsers is not that common anymore, and it was indeed very dangerous. It's still quite dangerous, although they have improved its security somewhat in recent versions. ActiveX is a Microsoft technology to run compiled code in Internet Explorer. It had a large history of terrible vulnerabilities, and it's also on the way out. I think it's still used by some websites, but people don't use it that much anymore. OWASP is an organization that people join and donate their time to. Every big company is in there. I'm a member. Most everybody in the security game is in here. They have good conferences and meetings, and one of their most famous projects is the Top 10 Project. Every few years, they publish a Top 10 web security vulnerabilities. And there are things like injection is always the first one, SQL injection, and other code injection, whereby just putting punctuation marks in fields, you can take over servers. And there's many other ones here, like sensitive data exposure and using incorrect forms of encryption and so on. Web application developers often consult this list to see how to avoid making the big mistakes. Extensible markup language is a standard way to encode documents, more universal in HTML, and service-oriented architecture is where multiple apps use the same service, so you send some kind of request to the server and you get a directory of services that are offered, and you can then choose among them. This is also how remote procedure calls work in Windows. So web services often use XML or JSON to structure these services. JSON is JavaScript. Object notation is just another way to record things. SOAP and REST are ways to request these objects off the server. And WDSL is the language you use to write a file that specifies all the services on your server and how they should be used. In databases, you have a lot of things stored like addresses and credit card numbers and so on. And the database itself can have a mixture of information at different sensitivity levels. And two of the attacks here are inference attacks and aggregation attacks. And we'll talk about them here. Anyway, a database has a primary key, like in government databases, it's often a social security number. At companies, it's your student ID or your customer number. And so this, because you can't use the name, there could very easily be two people with the same name. So you assign them some unique numbers, you know who you're talking about, and then you have records that are all keyed to that primary key field. In polyinstantiation, you have one row with two rows with the same primary key, but people at top secret see everything, and people at secret will only see some of the data in the record with that primary key. That's called polyinstantiation, where the database delivers different data to different security levels. Inference attacks are where you can use low-level information to deduce high-level information, and that's what I said. You can watch the number of pizza orders at night, and you can deduce when a military operation is happening in the Pentagon. So aggregation is a similar attack where you combine many low-level facts to deduce restricted facts. You could look up all the numbers in the public directory, and you could find what numbers are missing, and those must be the private phone numbers. That's an example of an aggregation attack. So to prevent these things, you would have to somehow increase the security of those low-level things, like make the pizza vendors conceal how many orders they had every night, and you could use polyinstantiation to prevent the other one. And you could even restrict the number of queries made. So no one is allowed to ask more than a certain number of queries in a period of time, so they won't be able to do enough queries to get a list of, say, all the phone numbers that are unclassified to deduce the others. Data mining is just searching for a needle in a haystack. So you have something like the whole internet, and somewhere in the internet there are the terrorists and whoever else you might want to find. So data mining is the task of searching a large database for something that's hard to find but valuable. And data analytics is another form of it, where you will look for use cases. There is software you can buy now that will supposedly watch patterns of activity on your network and decide which of your employees are disloyal. This is because of Edward Snowden. Edward Snowden was a trusted contractor for the military, the NSA, and he leaked out their secrets. And everybody then went to their manager and they said, how do we know there isn't another Snowden among us? And there's really no good answer. I've been told that inside the NSA, they now make every system administrator take a polygraph test every 3 months to try to find out if they're becoming disloyal. And people imagine that somehow you could monitor your network traffic and tell who has become disloyal, but this is very unclear how much you can do about that. So countermeasures for these things, you can have multiple overlapping controls so that even if one person decides to break the rules, they'll find other barriers, administrative controls, technical controls, and physical controls. You've got mobile devices. People are bringing in thumb drives, iPhones, laptops. They can be bringing in malware. They can be copying your files and taking them out. The fact that everyone is carrying such powerful computers introduces a whole lot more threats. So you can try to restrict the use of mobile devices and tell people they can't use them. In practice, your valuable employees will not tolerate this anymore. They'll just go work somewhere else. You can try to limit how much USB drives are allowed to be used. You can use only trusted devices. There are various software and standards you can use to label the official company devices and tell them from unapproved devices. These are all options that are available. If you don't want people stealing your data, and you can have backups of it on mobile devices, at least that means if someone steals the mobile device itself, you will have another copy of the data. There are two issues when someone steals a mobile device. One issue is you lose the data that was on the device, and a backup addresses that. The other one is the crook now has your sensitive data, and the thing that prevents that is full disk encryption. So even if they steal an iPhone, they won't be able to get in without the access code, and any more than the FBI can get in. There's also remote wipe, where when the thief turns the device on and connects to the network, you detect that and erase it from the server. But in practice, remote wipe fails quite frequently. A lot of devices are stolen or lost, and they never do again connect to the network, so you cannot prove that you wiped them. All right, and I say we can't do these either. I think that might be the end of it. It is the end of it. So there are two Kahoots that we'll do next time. And I think that's it. Like I said, this one's a bit longer, and next one will be a bit long too, but I'll hopefully have the Kahoots ready. Are there any questions or anything? I open up my chat window just to see if anything is happening. All right. Well, I guess that's it for this time. Next time we will meet at the regular time is my plan. I will be meeting at 9 p.m. in some hotel in Rochester, but hopefully I'll be able to do the class from there. Okay, folks, have a good week. I'll do it again next week. I'm going to stop the share. Okay.